The following presentation was recorded at the 2025 Southeast Linux Fest in Charlotte, North Carolina. It is licensed under a Creative Commons license. For more information on the Southeast Linux Fest, visit www.southeastlinuxfest.org. Come join us next June.
Hello. My name is Cameron Conn. Yours is not. This is, you should build your app with Zig. So what is this? Zig is a programming language. It is a low-level programming language, just like C. And this isn't going to be a talk to like give you a 30-minute guide like, oh my God, I'm so good at Zig. No, it's just an overview, sort of motivation about it, what you would do with it, how you can use it in production or to maintain your old code bases. So really quick, just if you have to leave for some reason, this talk in 100 seconds. Zig has no magic stuff in the background. It's got no macros, so it's all one language. There's no hidden control flow, like there's no C++ pointer where you overload an operator, it goes off to some crazy class file somewhere. No, it's straightforward. What you see in the code is what you get in execution. Zig is low level with manual memory management, so you have to manually allocate and free the bytes, just like C. And Zig has really good cross-compilation for like ARM, RISC-V, S390, if you know what that is. And it can compile both Zig code and C code. It's semi-memory safe, not really. It has some bounds checking array, but you can bypass that if you really want to. And it's got some cool features like comp time, so you can run code at compile time and not do like a script, do some call out to build some binary somewhere. No, you can just run Zig code at compile time. It's got really good error handling facilities, cleanup facilities, and it does some cool stuff with vectorization and SIMD in code. So Zig is basically C, but it's better. So this talk is really what Zig's trying to do, why you would use it, why you wouldn't use it, how you can use Zig to like maintain your old C code bases. And this is not an in-depth course or guide on Zig. If you want that, you go to ziglang.org, and that's a much better way to learn it than watch some lecture. So first off, this is talk about Zig. And if you like programming languages, you're a nerd. But if you look at this meme, conspicuously absent is Zig. If Zig is your favorite language, then you're in this talk and you're incredibly handsome or beautiful and intelligent. So, disclaimer first, before we dive into everything, you shouldn't use Zig. It is alpha quality software, and unless you hate life, you're frequently going to have broken code in your build system. Like I have a project that is like a debugger I started in like Zig 08, we're now at 0.14. The build system on that's broken like 3 different times. There's also like just APIs in the standard library just break. Another issue you wouldn't use Zig is like there's no resources anywhere online. It's like they're very few and far in between. Usually they're good, but also it's a lot of the older stuff now is broken because the language changes so frequently. The other reason you wouldn't use Zig is because there's compiler bugs. I've been bitten by this several times. Usually if you do C, when you have an issue with your code, it's usually your fault because you're stupid and you're a programmer. And it's not the compiler. But with Zig, instead of like a 99-1, it's like a 50-50. You're either an idiot or the compiler's broken. Other reasons you want to use Zig, there's no Stack Overflow protection. So if you go to forward recursing, you just blow up your program and you'll never know about it. And also, there's some stuff is not fully baked yet. So like the async functions in Zig, they removed because they were just broken for a while. So that's why you wouldn't use Zig. We're also going to skip a lot of stuff here just because of time. So one of my favorite things that you can use for like if you're writing AI inference, you can use SIMD vectors. So you can do like AVX 512 just in code without writing any assembly, which is awesome. I skip enums, tuples, and a whole bunch of other stuff that I can't even mention. Just for, if you want to know more, go to the actual website, read the docs. They're going to be much better than me. It's just something to whet your appetite. So first part, we're going to go into, show you a little bit of Zig, what it can do. So first, the Zen of Zig. Inside of the Zen compiler, if you run Zig Zen, it'll show you the Zen of Zig. Bring that up a little bit. So this sort of is like the motivation of the overall philosophy of the language. So one big thing is runtime crashes are better than bugs. Zig has a lot of facilities built into the compilation tool chain where it will, stuff that would be a bug, it'll just crash at runtime rather than silently keep going, which is very useful if like you have a server serving out HTTPS requests. So rather than going out of bounds on a memory read, it'll just crash rather than giving out your TLS certificates like a Heartbleed situation. And it also will do some stuff like it will check for overflows for integer operations, or for it'll also check for like truncation, and sometimes it'll check for subnormals on floating points. Another thing is a lot of stuff in Zig you can do at compile time. And if you can stop a bug when you compile the code rather than ship it off and see it whenever you're trying to run your program, it's just that much quicker. The other thing are these 2 points. Memory is a resource. This is very big if you work on embedded systems like me, or if you work on memory constrained systems. Freeing memory always works, but if you try to allocate memory, it can fail. Now, in C, you don't usually check for malloc failures, but in Zig, it's like required because it's built in the language. So let's look at some of the syntax. So Zig looks a lot like C. You've got your function declarations, you've got your return types, you've got your printf debugging. Here we see some of the memory allocation syntax. Don't worry about that for now, we'll go into that later. We've got this try keyword. You can concatenate 2 strings. And so what does it look like when you run? Or if I can run the right command. So it's a lot like Rust, where there's a built-in build step, where you can just do Zig build and then what you want to do. Whereas in Rust, it'd be like cargo run or whatever. So Zig is a lot like C. You have this same type of integer type. So instead of like doing a uint8t, an int64t, in Zig you do a u8 and i64, so that's list typing for your fingers. Bools are the same. Instead of calling it a float, you call it an F32. Instead of a double, you call it an F64. You call strings in C, which are null terminated. They're this in Zig, which is the open brace :0 u8. That's just a null terminated slice of bytes. I now see that there's some duplication on the slides, awesome. But you also have a lot of the same logical and bitwise operators. But in Zig, the logical AND is actually just English AND. Same with the double bars, it's just OR. And the function calling syntax is the same. So where things start to differ with Zig and C is that in Zig, numbers they can have an arbitrary width. So you can have all your standard stuff like a U8, an I8 for a unsigned 8-bit and an signed 8-bit integer. You can also have arbitrary width. So you can have a 7-bit integer. You can have a 2025-bit unsigned integer. You have a 1037-bit unsigned integer. And you can do that all the way up to 2 to the 16th or 65535 bits. For floating points, you can only have these 5 types. There may be new ones in the future, but these are the 5 types that are supported now. Also with numbers is that, unlike C, you have to explicitly convert and cast from integer to float and float to int. So if you want to go from a float to an int, you call this funny looking function where it's @sign int from or float from int, and you give the argument of an integer, and it'll convert to a float. And if you want to go the other way, you go from int from float. It's just a function call. And these are called built-ins, but they behave just like any other function in Zig. Now, what things also start to diverge is safety. In Zig, numbers are safe by default. And if something were to overflow or to underflow in Zig, it would actually throw a runtime exception. So what does that look like? So here, we have just a simple program that'll add the numbers from 1 to 10, and it'll multiply the numbers from 1 to 10. And then it'll do the same thing for 1,000. So here we just iterate all the numbers. This is the range syntax in Zig. It's 4. You go from 4, 1 through n, give I, add to s the value of I. So if we go 1 through 10, s at the end will have the sum of 1 through 10. And the same thing with product, it's just, now it's a star. And does anyone here, just blurt it out, does anyone here know the issue with this? Sort of hinted on it. All right, so for small numbers, this isn't going to matter. But for large numbers, say 1,000, this product function is going to overflow. So what does that look like in Zig? So it will compile, but we're going to see whenever we try to do our sum or product of 1 to 1,000, it's going to integer overflow. So Zig actually will look at it'll generate code, and it will check for the overflow. And if it's going to overflow, it will runtime panic. So this is going back to the Zen of Zig, which is runtime errors are better than bugs. So we're crashing the program because it wouldn't do something we didn't want it to do. So we can explicitly override this. If we just change this to the version that says I can overflow, which is equivalent to this. All this as just says treat this as a integer 64 because this is technically a U size, this I value. And so now the program will actually run, but it has a bug in it. It will underflow and we'll get 0 at the end. So Zig saved us there, and we had to explicitly opt into the unsafe behavior. Hey, I know what I'm doing, please underflow. The other thing is Zig likes C as pointers. We're not really going to go into this, but you say something's a pointer, just with a star, just like C, and you take the address of a value with another ampersand. And in Zig, there's no null pointers. So the $1 billion mistake Tony Hoare did, not in Zig. Zig's also has got just the standard control flow operators, if, while, for. We sort of saw that a second ago. And difference with Zig and C here is that you can break on labels within loops, or within functions. And you can iterate, instead of doing int I equals 0, I less than 10, I plus plus, and then do your for loop, you can just do for 0 dot dot 10 to go over 0 to 10, which is a nicety of Zig. Arrays in Zig are very similar to arrays in C, except arrays are only whenever you know how long the array is or how many elements are in your array. So if you have an array of 10 integers, it's always going to be that 10, and you can't cast to it at runtime. You will know that at compile time, and the compiler will just assume that it's always those 10 integers. Whereas slices, sort of like Go, is slices have a pointer, and then they have a runtime known length. So you don't know what it is till the code runs. It could have 0 elements in the slice, or it could have 2,000 elements in the slice. You don't know till at runtime. And in Zig, you can, just for ease of use, you can coerce arrays. So you can coerce compile time known sizes, lists of elements into a runtime known list, but you can't go from runtime to compile time known. So what does that look like? So this is the slice syntax in Zig. We import our standard library at the top, define our main function. We have a string here. We print out the whole string. Then we take a slice of the world word, which is sort of similar to Python, where you have your indexing operator and you have a range. Then we just print out world. Then we, at this offset, which is 14, which is these numbers up here, we go over all those characters and we print them, then we do a new line. So we do this. It will print out our whole message, print out our index 7 to 12, and then print out our numbers. So earlier I mentioned that Zig had bounds checking. So one of the things in C is you can easily do is you could easily go out of bounds with this array here. So like say if instead of going 0 to 10, for some reason I thought 20, I had 20 characters there. Well, in Zig, this is an error. Whenever you try to do that, it's going to panic and say, hey, you touched out of bounds. And the nice thing is it'll tell you the line number, and it'll tell you how long that list was, and at what index it was. So this is very nice for debugging. So something that you can easily fat finger and see, it's just Zig tells you, you messed up, here's where you did it, dummy. Also, I'm just sort of gloss over this, is just like C, Zig has unions and structs, where the nice things about Zig is you can tag a union. So when you can say, hey, I have this enum. This member you can only access it whenever this value of the enum is set, and Zig will prevent some type confusion errors with that. There's also optional types in Zig. So instead of like in C where you return from a value and you check if there's like a negative number return value, like int if you're trying to open a file, in Zig you can just return null or none, and there's language facilities that'll help you with that. I'm not going to talk over that in this talk just for time, but it exists and it's very nice whenever you have it. And once you have it, you're going to be like, how did this ever work without this? Another nice thing about Zig is, we'll see an example of this in a second, is you can defer cleanup work whenever you exit a function or whenever you exit language scope. So like if you have curly braces just in the middle of a function, whenever you exit those curly braces, it'll run some cleanup code. So like one of the common things with C-based and C-like programs is like you'll open a file, they'll do some work, and then you'll just leave the file handle open. And if you have a long-running like server, you could over time just stack up file handles and eventually exhaust the file handle open on your server. So what do you do that? Well, in Zig, you just defer file close, and remember from the Zen of Zig, resource freeing can't fail. So whenever you close that file, it just frees up, and you don't have to worry about it anymore. And so you're not leaking resources. Also, another thing in like C, whenever you error out, and like if you're to open a file, you do some operation, and then somewhere there's an error in there, like the file is corrupt, usually you'd have to like do go to cleanup, and you have some cleanup epilogue at the end of the function. Well, in Zig, you can just say, hey, if I have an error, only run this alloc.free if there's an error. So that also helps with resource cleanup. Whereas you'd have to manually do that in something like Go or C. In Zig, you just do error defer, and it fixes it and cleans it up for you. So how do you handle errors? Well, in Zig, unions and return types we've seen in so far, they can begin with a bang, which just says this is an error union. And what that is just internally, it's a union. There's one field that says error, and there's another field which is like the actual defined return type. And just as a nicety, Zig gives you this try keyword where, hey, run this function. If there's no error, just give me the return value. But if there is an error, quit this function immediately and return the error to whoever called me. And so you'll bubble up errors that way. And so what does that look like? So here I just have a method that says read a number, and I'm reading it from this file, num.txt. Now, and also defer that num.txt whenever it closes. So what this line 11 is saying is open this file if it exists, but if there's an error opening that file, immediately return with an error to whoever called me. Immediately after that, I say, hey, when I'm done with this entire function here, go ahead and close this file. And then I just have this buffer, read from the buffer, from the file, and then try and parse if there's an integer there. So if we go inside source, we look at our file, we see it's 1234 in that file. And so the happy path is if I run that error method, it just works and it reads 1234. So it read it parsed the number, it returned 1234, and we printed it back to line 6. But what happens if there's an error in here? Well, in C, I would have to like heavily manually have some cleanup whenever it detects an error. But let's say, let's do something, let's be mean here. Let's move this file where it doesn't exist. So if I run this again, it'll show, hey, there's a file not found because I just renamed the file. So if we move the file back, it'll work again. And y'all can all read that, right? Okay. Now let's say, okay, what if instead of failing here, I failed here? Let's say I echo Linux into num.txt. Now if I look at that file, it's now not a number, so it should fail here. So when I run this, I will get invalid character because the first letter of Linux, L, is not a character. It's not a number. Excuse me. So it errors out, propagates the error, and it quits right here. It never gets to here because it immediately returns with try. So this should just give you an idea of like, hey, I'm early returning this error, and that's just one of the niceties of Zig. Next is memory management. So memory is like a big thing on resource-controlled systems, and Zig does it a little bit differently, and it sort of helps you a lot, but when you don't really realize it. So unlike C, there's no malloc in Zig. You actually have to manually define an allocator, start the allocator, and then alloc free, call the allocator, and go, give me this, many of this, and then free it manually. But it's not actually that bad because allocators will let you do like, hey, I know I'm about to allocate 1,000 numbers and I'm going to free them all at once. So maybe I should use an arena because it's cheap to do that. Or maybe I always know I'm going to only have 100 numbers or something that I'm going to allocate. Well, then you can use a fixed buffer because you know exactly how many you're going to do. You may as well just allocate that at compile time within your executable. So what does the Zig memory API look like? Looks a little bit weird at first, but it's not too terrible. So here we define a general purpose allocator. We deinitialize it. Then we get our allocator instance. Then we call this first alloc method. So this sort of method signature, where we pass in the allocator into the Zig function, is actually the recommended way to do this. So it's weird to pass in the allocator when you first see it, but it starts to make sense because then you can manually dependency inject your allocator into a third-party library or some other static executable, or even put in the libc allocator into your Zig function, and you can sort of control at runtime, like, hey, which allocator I want to use. So the API for actually allocating and freeing is you do alloc.alloc that says, hey, I want 32 32-bit integers. I go over, I do some work on them, then I free it. Really, this could also be done up here because this is run at the end of the function. And then the second function shows what happens whenever you leak memory. So in Zig, just with the general purpose allocator, well, there may be other allocators that do this, just I know general purpose allocator does, is it will actually tell you when you leak memory because you're being a dummy. So whenever you alloc and you don't free, it will actually yell at you. So if we do Zig run mem, we're going to see memory address at this address leaked, and that is line 22 of our example, where we call alloc.alloc, and we don't free it. So if we look at line 22, sure enough, we do alloc.alloc. So how do we get rid of this? Well, we actually free it. So when we do this, no more leaks, no more problems, and the return value is 0 because it ran and it didn't leak. That's what the memory API looks like. It's a little bit different at first, but once you start using it, it makes a lot of sense. So also in Zig, I'm not going to go over this, just you can break out to assembly. Use the AT&T syntax, which is kind of ugly. It's not the one true Intel syntax, but you can do it. So one of the cool things about Zig 2 is you can run code at compile time. And it's not like in a makefile where you like have a phony build target and you call a script and you output some file. No, you can actually run Zig code from your source code at compile time. So you can do stuff like read an input file, hash it, embed it in your executable so you can check it somewhere. You can create up a lookup table for CRCs. You can do all sorts of things. And actually in Zig, you can define generics at compile time. And actually a lot of the standard library, it provides functions that are comp time run that generate structs that you can use as like an array list. So what does that look like? So this is compile time Fibonacci. So whenever you run this, remember this code actually runs at runtime, except for this print statement and this print statement. And you can look at the object code and dump it if you don't believe me. And this just says, hey, I have a expensive comp time function. Don't time out the build. So when I run this, it's just Fibonacci. It's going to do what you think it does. And it'll just print out Fibonacci numbers. But this is run at runtime. And if you have like any sort of table generation in your code for like JPEG decoding or for like AES table construction, this is really cool because you no longer like generate huge freaking files. You can just call a function and run it at comp time. And this is all done with this comp time keyword, which just changes it so the scope of this function runs at comp time. So I do have to warn you, comp time doesn't work with everything. It's kind of like function coloring with async, that famous paper, where it does sort of change the color of your functions. You can't do everything at comp time. Like you can't call out to a network server and pull a file. It has to be on your local system within the file directories. You can't like hit a PID at comp time either. It's just, if it's like a file in your system, generally you can do it at comp time. So that's the end of the Zig part. And now we're going to start going into the Zig executable part in like the compiler toolchain that Zig ships. So first off is, you've already seen this a little bit in this talk so far, but how do you run Zig files? Well, you just do Zig run, then the file name, and it just runs. You can also do Zig build if you're in a project, and that will use this build.rs file that exists, or this build.zig file that exists. It got rust on the brain. If you just do Zig build, and you do a target, it will pull from that build.zig file and run it. So what does that build file look like? It's just more code. It is another DSL, but it's just Zig code, and there's no special restrictions on this. You can do anything you want to at compile time within the build Zig file. So here we define our target and optimize targets. So if you like want to cross compile, you could do that here. We define a module for our code. We say here's an executable. Plot this in our build system and our output path. Run it. Write a command to run it, and say this running depends on the executable getting plopped out. And it all happens when you do Zig build. Another nice thing about Zig is it is incredibly easy to cross-compile. If you've ever had to cross-compile something like an ARM64 binary from an x86 desktop, you will understand how big this is. You don't have to download 20 freaking gigabytes of toolchain to cross-compile for ARM or for RISC-V. You can just Zig build, detarget, then a triple for the architecture you want to go to, and it just builds it. And Zig actually supports everything the LLVM toolchain does for targets. And some of the more exotic ones are here at the bottom, the NVIDIA PTX target and the GCN architecture for AMD. So what does that look like? If we do Zig build d target RISC-V 64 Linux muscle, then just with a standard executable, if I look at file zig out, then you see this is a UC Berkeley RISC-V executable. No tool chains, it's just the regular executable. If you've ever cross-compiled something, this will be crazy to you. But also, Zig doesn't just compile itself to a language nobody uses, Zig. It can also compile C, and it will also cross-compile your C to all the same build systems. This is huge. You don't download 20 gigs of toolchain. You can just cross-compile by setting the target triplet. And people actually use this in prod. Uber uses this in their monorepo at prod, and they have a support contract with the Zig Software Foundation just for this part, the Zig CC part. And so how does this work? Zig includes Clang inside of it, and it's a hermetic toolchain just packaged inside Zig. And you just do Zig CC, and you can cross-compile. So this is what it looks like when you cross-compile for RISC-V. We did just sort of do this. I'll do it again. And so if I run this in QEMU, it works. It's still RISC-V executable. So you can cross-compile Zig very easily. You can cross-compile code you already have very easily. What else you can do? Well, Zig can actually help you get rid of all your C code too. Zig ships with this tool called Translate C, and it will automatically translate your C to Zig. And it will use a built-in linked libc whenever it executes. And it does, so I sort of lied to you earlier, Zig does have a malloc method, but it's inside libc for compatibility. So what does that look like? So here, I have a little word count program taken from the GNU CFlow. Basically, it just does word count. What does it look like? If I GCC word count, if I word count the word count program itself, I get 141 lines, this many words, this many characters. So what I can do with Zig Translate C, I link libc, I say wc.c, and I pipe it out to wc.zig. It will translate that word count file to this ugly machine-generated Zig code. But it works, mostly. You do have to do some minor changes. There's like a 12-line diff. Exiting Vim. Extreme Programmer Challenge. So if I do this, or no, it's target. Then I do a diff of this broken Zig file with the fixed file. It's like 20 lines. And this is due to, on the, in the main method, the C compiler will actually, or the C runtime will take these int C and int RV and it will place them there. So when the process actually starts, those aren't actually there. And the runtime for C will actually place those there from the heap, from the process environment. But generally, I promise this is the same, and all the code will be here at the end, along with the slides. But it's basically the same code. It's just like a 10-line diff, just for this. So basically, you can take all your existing C, do it into Zig, and hopefully remove some bugs and fix them at compile time or at runtime, do some bounds checking. So we know how to do translate Zig to, or C to Zig, how to cross-compile with the Zig executable or the Zig compiler. But you can also do builds with the Zig compiler. And I've sort of shown that here and in this build.zig file. where you can define modules. You can tell the compiler to say, hey, I want this to be a dynamically linked library. I want this to be statically linked. And you can specify all that here. You can pull in third-party dependencies through an HTTP tarball, a tarball fetched over HTTP, and all sorts of stuff. So you've already seen this before, and we've already looked at the build.zig file, but I'll do it again. And that's like cargo build, type same thing. But so whenever you build software, you also need to test it, unless you're Microsoft. So with C, you would need to have like some sort of external testing framework, like Google Test or CPP check. With Zig, it's just built in. So if we look at this tester.c file, we see here that we've got our standard library. We've got our Fibonacci example from earlier. And we're doing these two checks where basically it's a unit test, or like JUnit or PyTest if you used that before, where we say, hey, if I call Fibonacci, I get the 10th Fibonacci number, is it equal to 55? Or if I get the 20th Fibonacci number, is it equal to 6765? And so the syntax for that is zig test and then the file. And it will build it. And then it will say how many test path. And this scales to as many files as you have. And you can have multiple tests in different files. And you can do it recursively if you have a large project. So, and what happens whenever your test fails? Just like any other test framework, Zig will yell at you, say, hey, this messed up. They'll say, hey, this was not what we got. I wanted 6764. I got 6765. It's on this line. And so just like everything else, so just like every other programming language, you can test with Zig. So it's batteries included, it's all there. So you can cross-compile Zig. You can cross-compile your old C code. You can translate it to Zig, deprecate your C code, and then you can test it and get rid of all your testing frameworks. So it's all built in. Zig is basically trying to replace C. It's not really going to happen, but it's getting pretty darn close. And so Zig does everything C does, but better. C is old and yucky, and that's the talk. Any questions? Yeah. Mike. I'll just repeat the question.
Testing. There it is. What's the value of arbitrary sized integers?
It's cool.
Okay. Because I mean,
There may be some use case, like some architectures, their word sizes, like in DSPs, digital signal processors, they'll have like a 24-bit word or something. But that's really all I can think of off the top of my head.
right, but I don't think there are any processors that have odd number.
No,
bits. No, okay.
I don't know of any either. But you can do it. We didn't think to ask if we should before we asked if we could. Got one more?
So, you said no null pointers, right?
No null pointers. There's an asterisk there, but it wasn't on the slides.
You did say C interaction, so
Yeah.
there's got to be some concept of null.
Yeah, so if you go to ziglang.org, C void, there's like a table showing you the Zig and the C version of stuff. So like you can do C pointers, and there's this sort of abstraction. There's this -C thing, and this is a C pointer, but it also has this dereferencing check where I'll zoom in on that. where you can do a C pointer in Zig, and it allows the address 0, but dereferencing 0 is safety checked, and it'll give you that runtime error that you saw a bunch in this presentation. So yeah, it's there, but it'll be caught by the user land before the kernel sees it and yells at you and does a seg fault.
So I'm an old C programmer, and I'm really struggling to wrap my brain around this. But you said I have to do my own memory allocation.
Mm-hmm.
So
the standard library gives you an allocator like malloc.
Right, but if I want to take my variable and I haven't allocated my memory yet, what does my variable of this pointer type have before I assign that allocation to it?
So you would generally, you'd have a slice or something for that. You have like an example of what you're trying to do?
Never mind. I didn't want to. I didn't want to go down the rabbit hole. But it's usable. You're saying it's usable. That's not a problem. You've never encountered a situation where you're going, why can't I do this?
I mean, yeah. What you can do is there's this optional type. And you can have an optional pointer. And optional pointers actually allow you to do null, but it guards all the accesses in a if unwrap. So you can have like a pointer, but like say you have like an optional field in a struct that's sometimes allocated, but not really. What it will do is you can have this optional pointer and it will just, hey, you need to unwrap this and check if it's null first, or if it's there, then you can mutate it.
Thank you. That helps.
Does that answer?
Yeah.
Okay, good.
Probably does. How about the roadmap? You say it's too scary to use right now, but when can we expect to be able to?
I say that because I have some issues with it, but it's alpha quality software. I built a cryptography library and an LLM inference in Zig from scratch, and the language has never been a hindrance. There's some stuff that's on the roadmap. It's all publicly available on the GitHub tracker. And right now there's actually a thing, this was in the extras part of the talk, but one of the things that is on the roadmap is self-hosted for debug builds. So there's different optimization levels you can do for Zig. One of those is like debug builds. Then there's release slow, or release safe, release fast, release small. Those do all what you think they do. They compile basically OS for small, O2 or O3 for fast, and then O2 for safe with those overflow checks. So one of the things for Zig is it wants to do self-hosting so it can get rid of LLVM and speed up the builds. Because like if I do Zig run main, you can see a lot of this time is this LLVM emit object part. And that's not the Zig compiler, that's LLVM being slow. So actually if I do this, build exe, you can see, again, this is just compilation, no running. That LLVM is still there. But one of the things in the Zig roadmap is this f no LLVM, where it will skip all the LLVM code emission, where it's just LLVM, and use Zig. And it does make fatter executables, or LSL main. So this is a 8.6 meg file whenever I don't use LLVM. But whenever I do use LLVM, it's going to be a lot smaller. It'll be a 3 meg file. So LLVM is nice there, and Zig is not quite as optimized as LLVM, which has like decades or tens of decades of engineer hours just in optimizing it in the code gen paths. But that's one of the things in the roadmap. The other thing is they want to add back async when it's unbroken. They want to add stack guards, which GCC and Clang have had forever, but that's something that's currently not in. You can just like smash your stack and I've got a ROPC oriented programming, and I've got a ROP attack in my server. So there's just hardening, cleanup. Most of the language is there, from what I understand. I'm not a Zig language developer, but I do write Zig code.
Thank you.
But that's the general roadmap. Good question. Cool, I did a good job, or I confused the hell out of everybody? Awesome.